So let's have a look at what we consider a difference of rates now, or problems involving difference of rates. So invariably, it's just something where the rate is increasing from one source, and then it might be decreasing from another source, right? So there's a couple of different versions of these. So let's have a look. Initially, we have a look at our input source, identify it, and subtract our output source. All right, so if we have a look here, we've got a radioactive isotope, decays at a rate proportional to the mass present at any point in time, at a rate of 2 m kilograms per year. Okay, the isotope is formed as a product of nuclear reactor at the constant rate of 0.5 kilograms a year. So it's forming at 0.5 and decreasing at 0.2. So my rate of change is the 0.5 increase, subtract the 2m decrease. All right, so there's the rate. That's my differential equation. In terms of solving them, it's always easiest to try and get them as a fraction. Okay, because to solve a DE of this nature, we're going to have to flip both sides and then integrate with respect to m. All right, so if we flip both sides, I get a nice tidy 2 over 1 minus 4m. Yeah. Integrate with respect to m, so I've got that log expression, derivative of the top times the bottom, so introduce a -4 on top, divide by -4 out the front, I bring the 2 out the front, deliver it with a -half, and I get that t is equal to -half natural log of 1 minus 4m plus some c. Whether you find the c constant here or a little bit later, it's just 6 to 1/2 does it. Often, if it falls out nicely, and in this one it may have fallen out nicely, if we'd have worked it out here, I could have said that at, wrong pen, at t equal to 0, m was equal to 0. Yeah, so in actual fact then I would have got 0 is equal to -1/2 natural log of 1 plus some c. And so we'll get c is equal to 0 in this case. So I could have worked it out there. All right. Instead, I just chose to rearrange everything. Bring the -1/2 across, the c across. Don't forget we end up with that -2 times -c, which is a positive 2c. So e to the positive 2c is just some constant, which we just represent as capital A. Rearrange our equation. I get m is equal to, put my initial condition in, and that's where I get my a is equal to 1. So it's an equivalent expression. Obviously, if m is equal to my expression here, to then determine how much isotope is present after 2 years, I substitute my t equal to 2. There's my exact form there, which is 0.245 kilograms. DE solver, really important that you practice these as well. So we just put in the initial DE, m dashed is equal to 1/2 minus 2m, put my condition in, and we get our equation, which is really nice. Put our t equal to 0. Sorry, our t equal to 2, we get our 0.245 grams or kilograms. Okay.